بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. أنا دكتور جمال عبدالواحد فرحان، أستاذ مساعد جامعة الانبار، كلية الهندسة، قسم الهندسة المدنية. أدرس تصاميم الخرسانة المسلحة للدراسات الأولية والتصميم المتقدم للخرسانة المسلحة للدراسات العليا. I am Dr. Jamal Abdulwahid Farhan, Assistant Professor, University of Anbar, College of Engineering, Civil Engineering Department. I am teaching reinforced concrete design for undergraduate studies and advanced concrete design for postgraduate studies. My lecture is design of one-way solid slabs. Introduction. A slab is a structural element whose thickness is small compared to its own length and width. Slabs are usually used in floor and roof construction. According to the way of transferring loads to supporting beams and columns, slabs are classified into two types: one-way and two-way slabs. If the slab is supported on two opposite sides, as shown in figure 1A. This is figure 1A. It will bend or deflect in a direction perpendicular to the supporting edge. The structural action is one way, and the loads are carried by the slab in the deflected short direction. This type of slab is called one-way slab. If the slab is supported on four sides and the ratio of the long side to the short side is equal to or greater than 2, as shown in figure 1B. This is figure 1B. Most of the load, about 95% or more, is carried in the short direction, and one-way action is considered for all practical purposes. If the slab is made of reinforced concrete with no voids, then it is called a one-way solid slab. While when the slab is supported on four sides and the ratio of long to short side is less than 2, as shown in figure 1C, this is figure 1C. For this case, the slab is called two-way slab. Since the loads on one-way slabs are transferred to support mainly in short direction, the main reinforcement is placed in that direction, while the long direction is provided by minimum reinforcement, called shrinkage and temperature reinforcement. For two-way slabs, the loads are transferred to supports in two directions, so the main reinforcement is provided in two directions, but it should not be less than the minimum reinforcement. Design of one-way slabs. To analyze and design of a one-way slab, a strip in short direction with 1 meter width is considered only, as shown in figure 1A. This is figure 1A, and a short direction and a 1 meter strip is considered in short direction. The steps of the design are as follows. Step number 1, determination the slab thickness. Based on deflection requirements, the minimum slab thickness is determined. Then this thickness is checked according to shear and bending requirements. According to ICI table 7.3.11, the minimum slab thickness is listed in table 1 below, where L equal to span length. Table 1, minimum thickness of solid non-pre-stressed one-way slabs. For simply supported slabs, the minimum thickness is span length over 20. For one end continuous, the minimum thickness is the span length over 24. For both ends continuous, the minimum thickness is the span length over 28. For cantilever, the minimum thickness is the span length over 10. Step number 2, calculation of the design loads. According to ACI code, the design load equal to WU equal to 1.2 dead load زائد plus 1.6 live load, where D equal to dead load per square meter in kilonewton over square meter units, while L is the live load per square meter in kilonewton per meter square units. Step number 3, analysis. The analysis of the slab to find the shear and bending moments at critical sections can be carried out using any method of structural analysis. The simplest method, thus frequently used, is the ACI coefficient method, provided that its limitations are satisfied. The shear and bending moments at critical section are shown in figure 2. This is figure 2. This is the shear diagram and the bending moment diagrams for critical sections. For shear diagram, the critical section is at the face of supports, here the face of the beams, while the moment diagrams are 3. Exterior negative moment at the face of exterior support, and positive moment at midspan, and interior negative moment at the face of the interior or at the first interior beam. The design moment according to ACI coefficient method at the critical section is M sub U equal to CWU, W ultimate, L net squared, while the design shear at the critical section is V sub U equal to C W ultimate dot L net, where C equal to ACI coefficient listed in figure 3 for bending and figure 4 for shear. L net equal to clear span of slab. Figure 3, ACI bending coefficients. For top figure represent the slab of more than 2 spans, while the bottom part of the figure is represents the slab of 2 spans only. The rows of the coefficient different according to the restraint of exterior support. The first row is for unrestrained support, like brick walls. The second row is for spandrel beam. The third row is for column. Figure number 4 represent the ACI shear coefficients at the face of supports. Step number 4, checking the slab thickness according to shear requirements. This checking is carried out by calculating the design shear strength phi V sub C, using thickness determined according to deflection requirements from equation phi V sub C equal to phi over 6 square root of F prime C dot B dot D, where B equals to 1000 millimeter, D equals to effective depth equals to h minus 25. Phi equal to 0.75. H equal to total slab thickness. Then, comparing the shear strength with the design shear force at the critical section, V sub UD. If V sub UD is less than or equal to 5 VC, then the slab thickness is adequate. While if VUD is greater than 5 VC, then the thickness is not adequate and it should be increased, and the above checking should be repeated. Step number 5. The maximum and minimum steel reinforcement. The maximum steel reinforcement permitted by ICI code is IS max rho max .B .D. Rho max equal to 0.85 beta 1 F prime C over Fy epsilon U over epsilon U plus 0.004 equal to 0.85 beta 1 F prime C over Fy dot 3 over 7, where B equal to 1000 millimeter, B equals effective depth and equal to H minus 25. Beta 1 is determined from 3 conditions. Beta 1 equal to 0.85 for F prime C less or equal to 28 MPa, megapascal. Beta 1 equal to 0.85 minus 0.05 F prime C minus 28 over 7 for F prime C is greater or equal to 28 and less or equal to 5. Beta 1 equal to 0.65 for F prime C is greater than 55. The minimal steel reinforcement, temperature and shrinkage reinforcement required by ICI code, ICI 7611 is listed in table 2. This is different for the value of yield stress of steel. This is equal to percent dot A gross. The percent is included in this table, where A gross area and equal to B dot H. B equal to 1000 millimeter, H total slab thickness. Step number 6. Design the flexural reinforcement. The area of reinforcement for critical sections can be calculated follows. IS equal to rho dot B dot D. Rho equal to 1 over small m, 1 minus square root of 1 minus 2 mr over Fy. R equal to mu over phi BD squared. Small m equal to Fy over 0.85 F prime C. The area of reinforcement should satisfy IS greater or equal to IS minimum, less or equal to IS max. Step number 7. Main reinforcement detailing. There are 2 methods for detailing the main reinforcement. The first, cutting off reinforcement method. Choose the diameter of bars, then calculate the spacing between bars at critical sections as follows. S equal to 1000 over N and equal to 1000 over AS over AB, where IS area of reinforcement for a strip of 1 meter width calculated in step 6. Area of the bar, AB area of the bar, and number of bars for a strip of 1 meter width. The cut-off points for half of reinforcement is shown in figure below. Figure 5. Figure 5, cut-off points for bars. The positive moments are cut at L1 over 8 or L2 over 8 for the first span and second span respectively. Here, 1/2 of reinforcement is extended and the other half is cut off. For the negative reinforcement, the bars extend for exterior support L1 over 4 and for interior supports L1 or L2 over 3. The exterior supports provide fixity, maybe column or wall, like the interior support, which is a column. Then the cut-off points for the exterior span is the same as the interior support. The cut-off points for at the exterior support is the same as the cut-off points of the interior supports. Another method of detailing is bending of reinforcement method. Choose the diameter of bars, then calculate the spacing between positive bars using equation 8. Half of bars are bent to the opposite side at supports to provide the negative reinforcement. This negative reinforcement is calculated using the following equation. Equation number 9. The provided negative reinforcement compared with the required reinforcement. If it is less than the required reinforcement, then additional reinforcement is added whose area should not be less than the difference between the available and the required reinforcement. The spacing of the additional reinforcement is calculated by equation 8 also. It is preferred that this spacing is the multiplier of the positive reinforcement spacing. The bending points for half of reinforcement is shown in figure 6. In Arabic, كمية الحديد المتوفرة عند كمية الحديد السالبة المتوفرة بعد انثني نصف الحديد الموجب يجب أن تقارن مع كمية الحديد المطلوبة. فإذا كانت كمية الحديد المتوفرة أكثر أو تساوي كمية الحديد المطلوبة فإن الحديد يكفي ولا داعي لإضافة أي كمية حديد إضافية. لكن إذا كان كمية الحديد المطلوبة أكبر من كمية الحديد المتوفرة فيجب أن نضيف قضبان إضافية عند المساند وبمسافات يفضل أن تكون من مضاعفات المسافات للحديد الموجب وذلك لتسهيل التنفيذ. The bending points for half of reinforcement is shown in figure 6 below. This is figure 6 for bending points. This is figure 6 for bending points. The bending points are L over 7 of exterior support, L1 over 4 or L2 over 4 for interior supports. If the exterior support provide fixity like interior support, then the location of bend point equal to L1 over 4 also. According to ACI code requirement, the spacing of reinforcement should satisfy as less or equal to 3h, where h is the total thickness, also less or equal to 450 millimeter. Step number 8. Design the reinforcement in long direction. In long direction, the minimum reinforcement, temperature and shrinkage is used. The required area of this reinforcement is calculated according to requirements of step 5. The spacing between bars is calculated using equation number 8. It's preferred to place this reinforcement over the positive steel at midspan and under the negative steel at supports to help in supporting the main reinforcement bars. According to ICI code requirements, the spacing of reinforcement should satisfy as less or equal to 5H and 450 millimeter. Here is an example. A reinforced concrete floor slab shown in figure 7 is built integrally with its supports and consists of 2 equal spans, each with a clear span of 4 meters. The surface live load is 2 kilonewton over square meter. The superimposed surface dead load is 2 kilonewton over square millimeter over square meter. Design the slab following the provisions of the ACI code. Use of prime C equal to 25 MPa, of Y equal to 420 MPa. Figure 7 show the floor slab which is to be designed according to ACI code requirements. Solution. Since L over S, long over short span, equal to 12.3 over 4 and equal to 3.075 greater than 2, then the slab is one-way slab. Here we follow the steps of design explained previously. Step number 1, slab thickness. From table number 1, H, the total thickness equal to L over 24 plus 1000 and equal to 166.67 millimeter. Practically, we use H equal to 170 millimeter. This is total thickness of slab. Step number 2, design loads. The dead load equal to the self weight of slab plus the additional or the superimposed dead load, and equal to 0.17 multiplied by 24 plus 2 equal to 6.8 kilonewton over square meter. While, as mentioned in the question, live load equal to 2 kilonewton over square meter. Thus, W ultimate, W sub U equal to 1.2 dead load plus 1.6 live load and equal to 10.5 kilonewton over square meter. Step number 3, analysis. Figure number 8 shows the bending moment and shear diagram. This is figure number 8. The shear force, the critical shear force at the face of the exterior beam and at the face of the interior beam, while the critical bending moments are exterior negative bending moment, mu1, called here mu1, and positive moment called mu2, and negative bending moment at the exterior face of the first interior support called mu3. In this slab, we need to design only one panel because of symmetry. Using ACI coefficients, figure 3 and 4, explained previously, the bending moments and shears are mu1, the exterior negative moment, equal to 1/24, this is the ACI coefficient, multiplied that 10.5, that 4 squared, 4 is the clear span, and equal to 7 kilonewton meter. mu2, 1/14 في 168 and equal to 12 kilonewton meter. mu3, which is the larger moment, the most critical moment, equal to 1/9 that 168 and equal to 18.7 kilonewton meter. The critical shear VU1, which is the design shear for the face at the face of the exterior support, equal to 10.5 plus that 4/2 and equal to 21 kilonewton. VU3, which is the critical shear at the exterior face of the first interior support, equal to 1.15 that 21 and equal to 24.15 kilonewton. Step number 4, checking the slab thickness according to shear requirements. The effective depth D equal to H minus 25 and equal to 145 millimeter. VUD means the shear at the critical section at D from the support, which equal to VUS. V sub US is the shear at the face of support minus WU dot D and equal to 24.15 minus 10.5 P.145 equal to 22.63 kilonewton. The design shear strength 5DC equal to 0.75/6 square root of prime C dot 1000, which is B, dot 145, which is D, divided by 1000 equal to 90.63 kilonewton, which is greater than VUD, okay, i.e. the effective depth, which is determined according to deflection requirements, is okay for shear strength. Step number 5, the maximum and minimum steel reinforcement. Using equation number 5, rho max equal to 0.85 squared, that 25/420, that 3/7. 25 of prime C, 420 is of Y. Rho max equal to 0.0184. From table 4, IS minimum equal to 0.0018, that 170, which is the total depth, plus 1000, which is the width of the strip, and equal to 306 millimeter squared over meter. Step number 6, design the flexural reinforcement. Using equation 6 and 7, the calculation of reinforcement is arranged in table 3 below. This table shows the values of rho and AS, rho that B that D, for MU plus, MU minus for discontinuous edge, and MU minus for continuous edge. Also shows AS minimum for positive and negative moment at that its continuous edge, the minimum reinforcement is control, which equals 306 square millimeter. Step number 7, reinforcement detailing. First, the method, the cutting off reinforcement method. For positive and exterior negative reinforcement of 5-10 millimeter bars are used then. S equal to 100, which is the width of strip, divided by N, and equal to 1000 divided by AS over AB, since N equal to AS over AB. Then S equal to 258 millimeter. For practical reasons, use 510 over 250 millimeter center to center. S equal to 250 millimeter less than 3H. Okay. For internal negative reinforcement, a 10 millimeter bars are used also. Then S equal to 1000 divided by N and equal to 205 millimeter. For practical reason, use 510 over 200 millimeter center to center. Also S equal to 200 millimeter less than 3H, which is equal to 510 millimeter. Okay. Temperature and shrinkage reinforcement along direction equal to 510 millimeter over 250 millimeter center to center. Reinforcement details are shown in figure number 9 below. The cut-off points locations are determined using figure number 5 mentioned previously. In figure number 9, the details of reinforcement for cut-off bars methods are shown. Bending of reinforced method. Half of positive reinforce is bent. The details of calculations can be arranged in table 4 below. Table 4, main steel reinforcement. For this table, first we calculate the reinforcement of the positive moment, which is 510 over 250 millimeter, which provide 316 square millimeter for strip of 1 meter width. Then half of this positive moment is bent. So the provided moment for exterior negative is 510 over 500. 510 over 500. It provides 158 square millimeter, which is less than the required reinforcement, which is 306 square millimeter. So reinforcement should be added. An additional reinforcement should be added. This reinforcement is 510 over 500 millimeter, which provide 158 millimeter. The sum of the provided and added reinforcement is 316 square millimeter, which is greater than 306 square millimeter. Okay. While for the bending moment at the interior support, the required reinforcement is 348 square millimeter. The provided reinforcement from the positive reinforcement is 510 over 250 millimeter, 50 square millimeter, which give 316 square millimeter, which is less than 348 square millimeter. So an additional reinforcement should be added. The added reinforcement is 5/8 over 500 millimeter, which give 100 square millimeter. The provided an additional reinforcement is 416 square millimeter, which is greater than the required reinforcement, 348 square millimeter. Reinforcement details are shown in figure 10 below. The bend points location are determined using figure 6, which explained or which mentioned previously. Figure 10 details of reinforcement for bending of bars and metal. Finally, this lecture is used for the design of the one-way slab. It can be used to design various of one-way slab. Thank you for your attention.